Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, we're back again, and we're going to continue discussing contact mode scanning simulations with VEDA. I've put together a number of simulations that perhaps will give you some insight into how the tip behaves when you raster the tip over different features in a substrate. So to begin, what you have to do, of course, is you have to go to the VEDA tool. There's a number of different ways you can do that. Perhaps the simplest way is just to go to the nanoHUB-U course page. There's supposed to be a link on that page that will take you directly to the VEDA simulation tool. When you get to the VEDA simulation tool for this lecture, you're going to have to select the contact mode scanning application. And all the examples that I'm going to run through were performed using that particular application. Again, let me say there are different ways this type of lecture can be given. We could possibly go through the VEDA tool in real time. I personally did not choose that option. Instead, I've focused on screen captures that have been annotated. So in my opinion, the best way to try to duplicate these simulations is to print out these slides and have the slides available to you when you go into VEDA and try to mimic the simulations that we're going to perform. When you open the contact mode scanning application, you'll see 5 tabs located across the top of the screen. These tabs are referred to as operating conditions and cantilever properties. In this tab, you have to specify certain parameters that relate to the operation of the instrument, the VEDA simulation tool. You also have to specify the cantilever properties. The second tab allows you to specify the tip sample interaction. You're allowed to choose whichever model for tip sample interaction that best fits your experimental situation. The third tab gives you the simulation parameters that are appropriate for the particular calculations that you'll be performing. This basically tells VEDA how many data points you want to take and gives some information about how the simulations are performed. In this particular lecture, the most important tab, in my opinion, is the tip sample interaction property features. Here we're actually going to specify localized features in the substrate that allows that the tip will scan over. And then lastly, the fifth tab is the simulate tab. That's where the actual calculations are performed. If you do a simulation and you do not choose to include tip dilation effects, the VEDA calculation typically takes a minute or so. If you include the tip dilation effects, the calculation takes a little bit longer, maybe 2 or 3 minutes. So my recommendation is don't select the tip dilation box at the beginning. Make sure that all the other parameters that you select are appropriate, and then you can go back and click the tip dilation, and you won't be wasting your time waiting for a calculation that's meaningless. So in the previous lecture, we considered how the tip scans over a sharp step. And what we learned in that simulation was that there's a large tip error, right? The set point conditions are not maintained when the tip first encounters the step and when the tip leaves the step after it just scans over the step. There's big errors associated with the Z piezo motion in those two extremes. In between, when the tip is scanning over the middle of the sharp step, the set point conditions are well maintained, and you've got an accurate representation of the topography. In this particular example, I like to just point out, if you scan over a smooth feature in VEDA, and the smooth feature will be selected by choosing Sinusoid in tab 4, right? You'll find that the tip never really catches up with the substrate geometry, and there's always an error between what the tip is, or what the feedback is, or I'm sorry, what the cantilever deflection is with respect to the set point, right? This is in direct contrast to the case where we scan over a sharp step. So let's just see how this plays out. Here's my first example. We're going to scan a tip over a smooth sinusoidal feature. The height of the feature is 10 nanometers. The width of the feature is 50 nanometers. These parameters can be set in tab 4. There's various operating conditions that have to be specified. So in this particular case, we're going to choose a cantilever with one eigenmode. We're going to choose a cantilever stiffness of 0.5 newtons per meter. Typical quality factor is on the order of 50. Typical resonance frequency for the cantilever is on the order of 40 kilohertz. The quality factor and frequency of the cantilever are not terribly important for contact mode scans, but they'll become more important when we do the dynamic AFM in part 2 of the course. We have to specify the set point deflection. In this case, I just choose 4 nanometers. So by choosing 4 nanometer set point deflection with a cantilever spring constant of 0.5 newtons per meter, that's telling me that my force set point is 2 nanonewtons as I scan the tip over the substrate. I choose 10 scan lines per second just to pick a number. The proportional and integral gains, I've adjusted those to be 0.002, and we'll look at those in a little bit more detail. We're going to choose the DMT contact model. We're going to select the modulus of the sample to be 100 gigapascals, and we're going to scan over 100 nanometer range, okay? So the questions are, what do we observe in the measured topography? And if we change the feedback gain, what effects does that have in the measured topography? So those are the questions that we want to answer immediately. Just to be precise, I include the echo input file for the calculations that I'm going to present in the next few slides. From this echo input file, it's very easy for you to check and make sure that, for instance, the parameters you set match the ones that I did. In that case, you should get an exact duplicate of the results that I'm going to jump through here in the next few slides. So the first slide is the result of the effect of the feedback gain on the so the first result here of the simulation is the effect of feedback gain on the fidelity of the tip as it scans over the sinusoidal feature. So the sinusoidal feature is indicated in red in this diagram, and I've selected 2 feedback gain parameters for P and I, 0.001 and 0.002. What you can see is that the feedback gain for 0.002 gives you a more accurate representation of the feature than a feedback gain of 0.001. And it would be your natural tendency to go back into the software and perhaps increase the feedback gain parameters to 0.003 in order to try and reproduce the sinusoidal feature even more accurately. When I did that, I found that the tip substrate approach curve took an exceedingly long period of time. It just basically means that the numerical software is having a difficult time approaching the tip to the sample. So I conclude that for this particular example, the optimal PNI for the system is 0.002. You can adjust the scan speed. You can allow the tip to raster over this sinusoidal feature with different lines per second, and the effect of the motion of the sample in order to keep the feedback loop at 2 Newton per meter, or 2 nanonewton constant force, right? The effects are shown here. So you always have to remember that in AFM, the topography is really the motion of the sample with respect to the tip, and the accuracy of that in terms of the real topography of the system, that's dependent on the parameters of the system that you're using. So this is very clearly illustrated here, where you can see if you try to scan over the sinusoidal feature at 20 lines per second, which is too fast, you're going to start to miss on the actual height of the feature. And in addition, the feature is going to be shifted with respect to its original position. So basically what's happening, of course, is that the tip motion is always being adjusted to try to track the sinusoidal variation in height. But the topography is always changing. So the tip really never catches up, right? And as a result, you've got these distortions in the topographic image that are quite evident with respect to what you've actually specified. In VEDA, you can print out the error in the topography, and I do that in this particular slide. I just trying to emphasize that the error is non-zero everywhere, except at one point on a smoothly varying feature. So this is in direct contrast to the square step, where once the transients damped out after the tip encountered the step, the error in the topography was 0 at the top of the feature. In this case, there's a non-zero error everywhere except at one point. After you do this simulation, these results are all for 0 tip radius. It's very simple to include the tip dilation, and I do that in this particular example so that I believe the tip radius in this example is 10 nanometers. So you have to go back and you have to enable the tip dilation software. This calculation runs a little bit longer, but you can see that if for the scan rate that I've chosen, the sinusoidal feature would be distorted. It would be actually wider than it actually is. It's also shifted, that's just due to the fact that the tip radius is non-zero. So this is just an example that you can work through and get some intuition about what new features are introduced when the tip scans over a feature in the substrate, which is continuously varying. There's no sharp edges in it. So just to emphasize that. It's possibly not obvious if you sit down and just think about this ahead of time. The simulation helps to bring out these different features. Very often, if you're making devices in, let's say, a silicon wafer, you are asked to image a trench in the silicon wafer. And so in that case, to mimic that case, I'll just show you how to work out a trench-like feature and show you how the tip tracks that trench-like feature. In this case, we're in tab 4, the tip sample interaction properties. The feature we're going to specify is a trapezoid, so you have to select a trapezoid. Once you select a trapezoid, you're then asked to specify the depth of the trapezoid, the width of the trapezoid, and what the taper of the trapezoid is. So those numbers can be specified, and I give you the values that I use in this particular simulation in this slide. Again, we have to set the operating conditions. We have to set the tip sample interaction properties. So in this case, I'm using the DMT model. Again, I'm using a sample which has 100 gigapascal modulus. That's a pretty hard sample, right? I want to run a simulation, and then with 0 tip radius, and then I want to include the tip radius and show you how the topography that the AFM gives you changes once the tip radius is included. So for this case, I'm going to use 10 lines per second. I'm going to have a 2 nanonewton set point force. That's what the Z controller is going to move the substrate with respect to the tip in order to keep this 2 nanonewton force constant. It's going to do as good a job as it can, given these feedback parameters for the proportional and integral gains. So the results of this simulation I just show on this particular slide. Here the red curve shows you the trench-like feature that I specified in tab 4. The light blue line shows you the result of the motion of the substrate with respect to the tip if the tip has 0 radius. So the deviation of the light blue line from the solid red line, that's indicating feedback control issues. It just means that the tip can't accurately track the substrate features for the scan line rate and for the feedback parameters that I set. When you include tip convolution, the simulation requires a little bit more time, but you can see that when you include the tip convolution, I think this is for a 10 nanometer tip, you can see that the width of the feature is grossly underestimated, right? And so if you're trying to adjust processing conditions to get a certain width of the step or a certain width of the trench, and you use AFM to verify the width of the trench that you've etched, this clearly shows you that you're gonna miss on the etching conditions, because you're gonna think that the trench is actually not as wide as you think it is, right? So the depth of the trench is accurately reproduced in AFM. In this case, the tip convolution causes you to miss on the width of the trench, and that's of course something that you have to anticipate when you do AFM. To characterize features that are etched into substrates. The third example I'd like to illustrate is what happens if you scan over a step feature which is very soft. So you can imagine depositing, let's say, step-like features on a substrate, let's say maybe using some sort of a polymer. The polymer is much softer than the actual substrate. So I think in this particular case, I'm using 100 gigapascals to mimic the substrate. The thin step-like feature that I'm depositing on top of the substrate is going to have a much smaller elastic modulus. In this case, it's 10 gigapascals. And I want to just see what the measured topography is going to look like in this situation compared to the actual topography that I specify. So I'll just show you the results of that simulation. So in this curve, in this slide, the red curve is the actual step-like feature that I specified. It's 0.5 nanometers high. It's got a modulus of 10 gigapascal. The flat substrate has got a modulus of 100 gigapascals, as I've indicated. When you actually scan the tip over the substrate, in this particular case, because the substrate is soft, right, the tip actually indents into the substrate, and this causes the measured topography to look like a trench rather than a step. So in this particular simulation, the measured topography of the step-like feature is actually a trench that's 0.15 nanometers deep rather than a step that's 0.5 nanometers high. So if you're not aware of the fact that the modulus of the feature is very soft, you would completely misinterpret the AFM image on topography, and you would come away thinking that you've actually produced a depression in the substrate when in fact there's a 0.5 nanometer high step there. So just an example of how you can be misled if you're not cognizant of all the details required to improve the accuracy of your scan. So the way to get around this, of course, would be to use a lower set point force when you do the scan. If you use a lower set point force, you'll eventually be able to reproduce the step feature. So if you, I include more details in the appendix than I can discuss here at this point, but I worked through a few examples to try to lead you up to this final result, which I just display here at this particular point in the lecture. So I'm about out of time, and I guess the next lecture, what I like to discuss is I like to systematically adjust these feedback gains, P and I, and try to give you a sense of how they influence the topography of an AFM scan when the tip is in contact with the substrate. So come on back and we'll discuss that in the 5th lecture of the 5th week. So thanks for your attention.